Welcome to my tutoring session in chemistry. The current video is part 3 of the 7-part series in HPLC. In this video, I'll explain the general features of instrumentation in an HPLC setup. And this will be followed by a detailed explanation about the detectors and methods that is commonly employed for the detection of components in HPLC. Now here's a figure depicting the schematic workflow of a typical HPLC setup. We have a solvent reservoir and the mobile phase of the solvent is transferred to this reservoir. Now before the solvent is transferred to this reservoir, it has to be filtered using a 0.45 or 0.2 micron membrane filter. And this is done in order to remove any particulate matter or impurities present in the mobile phase of the solvent. And this will be followed by the ultrasonication that removes air bubbles from the solid system. So filtration, membrane filtration first in order to remove the particulate matter or impurities, followed by ultrasonication to remove the air bubbles. And now the solvent is introduced into the reservoir. Now the solvents used for HPLC technique should be of analytical grade, and HPLC solvents are commercially available. Some of the polar HPLC solvents that are commercially available are water, methanol and acetonitrile. A degasser removes any dissolved gases in the mobile phase. It removes dissolved gas like oxygen and nitrogen. And this can be accomplished by purging helium gas through the mobile phase. And by doing that, the helium gas, it displaces or removes the dissolved gases like oxygen and nitrogen present in the solvent. A high pressure pump, it delivers the solvent from the reservoir onto the column. A pulse dampener is located between high pressure pump and the column. The functional role of a pulse dampener is to dampen the pressure fluctuations generated by the high pressure pump. So basically the pulse dampener, it smoothens the pressure fluctuations caused by the high pressure pump and makes sure that the solvent or the mobile phase flows through the column at a precise and controlled flow rate. Now first the mobile phase, it enters a pre-column. The reason for this to be called as pre-column because the mobile phase enters this column, small column, before it passes through the analytical column where the actual separation takes place. And finally it is eluted out of the column. Now the pre-column is also called as guard column as it protects the analytical column from particulate matter or impurities, and thereby it increases the life of the column. It is also called as pre-filter as it filters out any particulate matter or impurities present in the mobile phase. Now the packing material is same both for the pre-column as well as the analytical column. Now the packing material is nothing but the stationary phase, which could be polar in nature or non-polar in nature. So only difference is in case of pre-column, because of its size, the amount of the packing material is less, while in case of analytical column, the packing material is more, that is stationary phase is more. Now the mobile phase, it enters the analytical column where the actual separation takes place, and then it elutes out of the column. The function or role of a detector is to monitor the elution process during the HPLC separation, and it detects any components that elutes out of the column. Now let's inject the sample mixture into the column using a multi-port valve, which is part of the setup. Now the sample mixture, it contains three components A, B, C molecules highlighted in different colors, red, blue and green. And the sample mixture with the components, it passes through the column along with the mobile phase. And during the separation process, these components travel at different rates depending on their relative affinity towards the stationary phase. Now the green component has greater affinity towards the stationary phase and hence it is retained in the column for a longer time, while the red component, which has weaker affinity towards the stationary phase or weaker interaction with the stationary phase, it elutes out of the column first as it is highly soluble in the mobile phase. So its interaction with the mobile phase is much stronger than the stationary phase and hence the red molecule elutes the column first. Now when the red molecule which has eluted the column first, when it falls in the path between the UV lamp and the detector, it absorbs the radiation given by the UV lamp, and the moment the molecule absorbs the radiation from the UV lamp, the detector, it generates an electrical signal that is amplified and recorded as a signal, which is seen as a chromatogram that is displayed in the monitor of the computer system. Now chromatogram is a plot of retention time on x-axis against the concentration or absorbance of the molecules against the y-axis. So retention time on x-axis, that is time taken for the component to elute out of the column, was the concentration or absorbance by the components on the y-axis. So here for the explanation, we are making use of a C18 column which contains a non-polar stationary phase. The standard structures what you see inside the column, the thread-like structures, they are the non-polar stationary phase. Now C18 column, it is so called because this standard structure, it is constituted by 18 carbon chain, aliphatic chain constituted by 18 carbons and hence the name C18 column. It is a silica bonded octadecyl group and is non-polar in nature. Now this column, which is tightly packed with the stationary phase, now the mobile phase, it passes through this column under high pressure. And some of the polar solvents recommended for Hplc are water, methanol and acetonitrile. So let's say we are using this particular mixture for the separation of the components A, B and C, and the components, they travel at relative speeds, different relative speeds based on their affinity towards the stationary phase or the mobile phase. So non-polar molecule interaction is greater towards stationary phase, while the polar molecule, its interaction is very less towards the stationary phase. It is highly soluble in the mobile phase as it is a polar molecule, and hence its interaction with the mobile phase is greater, and hence the red molecule elutes out of the column first. Whereas the non-polar molecule with stronger bonding or interaction with the stationary phase, it is retained for a longer period in the column, and hence it comes out of the column last. Now the Hplc technique, it is known by two names, high pressure liquid chromatography and high performance liquid chromatography. So it is called high pressure liquid chromatography because of pressurized flow of the mobile phase. Now the operating pressure is usually high, it is around 1000 to 8000 psi. Now reason for this high operating pressure is due to the small particle size of the stationary phase, which is around 1 to 5 microns, and the column size, which is very narrow, and also due to tight packing of the stationary phase. So all these three factors, small particle size, narrow column and tight packing of the stationary phase, all these three factors, they operate together and offers a greater resistance towards the flow of the mobile phase. And it's also called as high performance liquid chromatography as its performance is superior or better as compared to the or in comparison to the conventional column chromatography, and also it has a very good resolving power in comparison to the conventional column chromatography. Now the Hplc technique is a versatile and powerful analytical technique used for analysis of non-volatile and thermally labile compounds. Now for the current separation, you are making use of a C18 column with a non-polar stationary phase. The mobile phase, it flows through the column at high pressure, and when the sample is injected via the multiport valve, the components of the sample mixture, it flows to the column along with the mobile phase. So here the mobile phase that is used is a mixture of water, methanol and acetonitrile in varying proportions. So when the sample mixture is injected into the multiport valve, the components, they travel at relative speeds as it enters the column along with the mobile phase. And during the separation process, you can see that the red component, because of its weaker interaction or affinity towards stationary phase, it comes out of the column first, while the non-polar green molecule, because of its greater affinity or attraction towards stationary phase, it is retained in the column for a longer period of time. So a non-polar molecule interacts strongly with the non-polar stationary phase. The rule of thumb says that like dissolves like, and hence highly polar molecule dissolves in the highly polar mobile phase, and hence it is eluted fast or comes out of the column first. Now before the components elute out of the column, the detector, it receives the radiation given out by the UV lamp, and therefore you get a baseline. So a baseline is seen in the monitor of the system, because during this process there is no sample injected into the column and the system is getting equilibrated, and there is a baseline seen and no peaks appear and there are no components coming out of the column. So in the absence of components eluting out of the column, there is a baseline, no peak. Now once the highly polar molecule elutes the column, it falls or comes in the path between the UV lamp and the detector, and it immediately absorbs the UV radiation given by the UV lamp. The moment the red molecule absorbs the radiation given by the UV lamp, the detector, it generates an electrical signal that is amplified and recorded, which is seen as a signal or a peak. Now this peak corresponds to the polar molecule, and the second molecule that will be coming out of the column will be the blue molecule, and when it falls in the path between the UV lamp and the detector, it absorbs the radiation given by the UV lamp and detector. It generates electrical signal. It's amplified and recorded as a signal, which is seen as a peak. So blue peak for the blue molecule. And the last molecule which is eluting out of the column is the non-polar molecule. It is retained in the column for a longer period of time because of its greater interaction with the non-polar stationary phase. And when it falls in the path between the UV lamp and detector, it absorbs the radiation and a corresponding peak is seen. Now the chromatogram is a plot of retention time on x-axis in minutes against the concentration or absorption by the components. Now what is this retention time, which is abbreviated as RT? So RT stands for retention time. Now retention time is the difference in time between the point of injection and the appearance of peak maxima. And this retention time is unique for each sample. So each sample has its own specific retention time value. And based on the retention time, you can identify the components in the given sample mixture, as the retention time is constant or specific for a given combination of stationary and mobile phase used in HPLC column. Say 0 minute is the time where you inject the sample, and after 1 minute you see the peak appearing for the red molecule. After 2 minutes you see the peak appearing for the blue molecule, and after 3 minutes you see the peak appearing for the green molecule. So retention time is the difference in time between the point of injection and the appearance of peak maxima for the respective molecule. And the parameter that is considered on the y-axis is the concentration or absorbance of that respective component in the sample mixture. So this figure depicts the UV detection of components in the HPLC based on their retention time value in minutes. So the detector generates an electrical signal that is amplified and recorded in the form of a chromatogram with a plot of RT versus absorbance or concentration. That is solid concentration as a function of time. Now there are three things that can be done using an HPLC. You can separate the given sample mixture into individual components. This is based on their affinity towards the stationary phase or interaction with the mobile phase. And secondly, identification of the compound. As I already mentioned, the RT values are constant for a given sample for a given combination of stationary and mobile phase. So based on their retention time values in minutes, you can identify a particular component and thereby carry out qualitative analysis. So qualitative analysis is nothing but carrying out the identification of the component in the given sample mixture based on their retention time values. And quantification, that is estimating the amount of the component. So estimation of the separate component is based on the area under the peak. Now you can see the area under the red peak is different from the area under the blue and green peak. So obviously, looking at the size of the peak, the area under the red peak will be more as compared to that of area under the blue peak, which is in turn less than the area under the green peak. So obviously the concentration of the red molecule will be more as the area under the peak is more. So estimation of the separate component is based on the area under the peak, and thereby you can carry out the quantitative analysis. So three things can be successfully carried out using the HPLC technique: separation of the given sample mixture into individual components, identification of the components based on the retention time values, and quantification, that is estimation of the separated components based on their area under the peak. Now moving on to the detectors used in HPLC. Now the detectors used in HPLC is purely based on the nature or property of the compounds being analyzed. Now the different types of detectors used in HPLC, or the commonly employed detectors in HPLC technique, are UV detectors, which operate at a fixed wavelength of 254 nanometers, variable wavelength detector, which operates with a wavelength ranging from 200 to 800 nanometers, which covers both the UV region as well as the visible region, refractive index detector, fluorimetric detector, conductivity detector, amperometric detector, and photodiode array detector. So let me walk you through these 7 detectors in a sequential order. Now fixed wavelength detector, it operates in wavelength of 254 nanometers. So why only 254 nanometers? Why not other wavelengths? The reason is most of the compounds absorb at this particular wavelength of 254 nanometers, and hence this particular wavelength is being selected. And the variable wavelength detector, it operates at a wavelength ranging from 200 to 800 nanometers, which covers both the UV region as well as the visible region. And this detector, it employs a deuterium lamp as well as a tungsten lamp. Now deuterium lamp is the source of UV radiation covering the wavelength range from 200 to 400 nanometers, while the tungsten lamp is the source for visible radiation whose wavelength ranges from 400 to 800 nanometers. Now the UV detectors, be it UV detector or UV visible detector, that is fixed wavelength detector or variable wavelength detector, both detectors work on the principle of light absorption characteristics of the sample. And why do the compounds absorb the radiation? Because these compounds, they bear a characteristic group called chromophores. So compounds with characteristic chromophores can absorb UV visible radiation and hence detected. Now UV detector, it operates at a wavelength of 254 nanometers. Now say for example, we are carrying out analysis of paracetamol sample, and this molecule is the analyte. It absorbs UV radiation at 254 nanometers. The major drawback with the UV detector is that if a molecule, associated molecule, it absorbs at a wavelength of 545 nanometers, it goes undetected because this impurity molecule that is present along with the paracetamol molecule that is being analyzed, it absorbs at a wavelength of 545 nanometers. But the fixed wavelength detector, it provides fixed wavelength of 254 nanometers, and therefore though the component, that is this azo compound, though it is present as an impurity along with paracetamol molecule, it goes undetected as it cannot absorb the wavelength of 254 nanometers, and hence no peak will be observed for the impurity peak. I mean for the impurity compound, that is the azo compound, as it is unable to absorb the UV radiation, and therefore you can see only the peak for the paracetamol molecule in the chromatogram and not for the impurity compound, which fails to absorb the radiation because it can absorb only in the visible region. So how to go about this problem? Now this drawback that you come across in UV detector can be overcome by using UV visible detector. Now UV visible detector, it provides wavelength ranging from 200 to 800 nanometers. So now when you carry out the analysis of the same sample mixture constituted by paracetamol and the impurity compound, that is azo compound. So as usual, the paracetamol molecule absorbs at 254 nanometers. A peak is seen, while the azo compound, it absorbs at 545 nanometers, which falls in the visible region. So UV visible detector is able to provide both UV radiation as well as the visible radiation. It covers both the region, and therefore you see two peaks: one for the paracetamol molecule, the analyte compound, the molecule which is being analyzed, and also a impurity peak. So the presence of another peak, the presence of the blue peak, it clearly mentions the fact that the impurity is present in this sample mixture being analyzed. So that is about the UV, that is fixed wavelength and variable wavelength detector. Now moving on to the refractive index detector. Now we have a non-polar stationary phase in the C18 column, and the mobile phase is flowing through the column at high pressure. Now normally, when only the mobile phase, when it flows through the column, the detector, it measures the refractive index of this mobile phase, and a baseline is recorded. So you see or observe a baseline in the monitor of your system, and baseline is recorded as there are no components in the column. Now when you inject the sample mixture into the multiport valve, the components of the sample mixture, it travels with relative speeds, different relative speeds, and it passes into the column along with the mobile phase, and it gets separated along to their, according to their relative affinities towards the stationary phase. So molecules of varying polarity travels varying distances, and it is a polar molecule which is eluting out of the eluting the column first, as it is highly soluble in the polar mobile phase. Now the detector, it measures the refractive index. Now the refractive index of the system changes. Why? Because the sample is changing the refractive index of the system. So detector, it measures the refractive index of both the mobile phase as well as sample together. Now it measures the difference in the refractive index between the sample and the mobile phase. And a peak is seen based on the difference in their refractive index. Now refractive index detectors, they are differential detectors and are designed to generate a signal that depends on the difference between the refractive index of the pure mobile phase and the dissolved solute. That is the component molecules that is being separated. And fluorimetric detector, as the name indicates, it has something to do with the fluorescence. So fluorescence of what? Fluorescence of the compounds that is being analyzed. So fluorimetric detectors, they basically respond selectively to fluorescent compounds. So only fluorescent compounds can be analyzed using fluorimetric detectors. And the detector is designed to respond selectively to fluorescent compounds. So excitation, both excitation and emission wavelengths can be selected for each compound. Now for each fluorescent compound, say for example, if you are analyzing quinine sulfate, now this quinine sulfate is a fluorescent compound, and when a radiation falls on the fluorescent compound, it undergoes transition from the ground state to the excited state. And this wavelength is called excitation wavelength. And when it comes down from the excited state to the ground state, again there is emission of radiation at a specific wavelength. Now this excitation wavelength, that is wavelength of radiation required to excite the molecule, and emission wavelength, that is the radiation emitted during the transition from the excited state to the ground state, they are specific for a given sample. So each given sample, it has a specific excitation and emission wavelengths. And this principle is employed for the fluorimetric detection. Now moving on to the conductivity detector. Now the conductivity detector is designed to respond selectively to ionic compounds. So only ionic compounds that are soluble in aqueous mobile phase can be detected by employing conductivity detector. Now the conductivity detector, it measures the conductance of an aqueous mobile phase containing ionic solutes constituted by cations and anions. The conductivity detector responds only to conducting ions like cations and anions. So we are employing a non-polar stationary phase using a C18 column, and the separation is carried out by reverse phase technique. Now in the reverse phase technique, the stationary phase is non-polar while the mobile phase is polar in nature. Now we are employing water as a mobile phase for the separation. Now the detector, it measures the conductance of the mobile phase containing water. So water is aqueous in nature. So we are using a aqueous mobile phase as water dissolves the ionic solutes. And when only the aqueous mobile phase flows through the column under high pressure, a baseline is recorded and is observed on the monitor of the system. Now when the sample mixture is injected into the column, the conducting ions, that is cations and anions, they travel through the column at relative speeds. And now the detector, it measures the conductance of the mobile phase. So now the conductivity of the mobile phase changes due to the presence of ionic solutes, that is cations and anions. So you get a peak. So the moment the conducting ions elute out of the column, you see the respective peaks for the ionic solids that is being separated. So here the principle of separation is purely based on the conductance of the ionic solutes, that is conductance contributed by the cations and anions of the given sample ionic compound. Amperometric detector. Now the prerequisite or the requirement for amperometric detector is that the molecule being analyzed or separated using Hplc technique, it should be having oxidizable or reducing groups. Now the molecule that we are studying is or analyzing is paracetamol molecule. It has both oxidizable as well as reducible groups. So it has two oxidizable groups, NH group and OH group, and one reducible group, that is a keto group. So the amperometric detector is designed to effectively measure the current produced by the electrochemical reduction or oxidation of the solutes when a fixed potential is applied. Now when a fixed potential is applied, what happens? These groups, they get either oxidized or reduced, and a current is generated. So the diffusion current so generated due to the oxidation or reduction, that is electrochemical oxidation or reduction of the groups, is directly proportional to the concentration of the eluted compound. So the requirement is that the compound being analyzed must have functional groups that can be either oxidized or reduced. So when a potential is applied, these groups gets either oxidized or reduced, and thereby a current is generated. And the generated current is directly proportional to the concentration of the eluted compound. And photodiode array detector. Now photodiode array detector, it provides us a spectrum which is a 3D plot of absorbance versus time versus wavelength. So the major advantage with the photodiode array detector is that it provides us with three different parameters for the molecule to be analyzed. That is absorbance of radiation by the molecule, time taken by the molecule to elute out of the column, and the wavelength at which the molecule absorbs the radiation. So it is a 3D plot. And the principle that it works is almost similar to that of variable wavelength detector. So a photodiode array detector can measure multiple wavelengths simultaneously, enabling it to capture the entire spectrum of a species in a single measurement. And the detector, it operates based on the same principle as that of variable wavelength detector, providing wavelength ranging from 200 to 800 nanometers, which covers both UV as well as visible region. And this efficiency significantly enhances the accuracy and speed of spectral analysis. Thank you so much for watching my video. I hope you enjoyed, and I'll meet you in my next interesting tutoring session.